fellow at Raytheon in their missile systems business unit. And he is responsible for working across many different programs and projects at Raytheon. And he is really responsible as a thought leader around innovations in the engineering practices at Raytheon. And we're so happy to have him here today. So come on up, Barclay, if you would.
Thank you. Okay, well, thanks, Debbie, and thanks to IBM for the opportunity. You know, I grew up in this area, and I've lived in the South most of my life. But just recently going out to Tucson and working with Raytheon Missile Systems, I found that people talk a little bit differently out there. There's different terms that people use for things. You know how this works? Different parts of the country, people call things different ways. So for example, in Tucson, this is called a river. That's right. And there is occasionally water in there, you know, in certain seasons. This right here is known as a lawn, you know, in Tucson. They all look like that. This is a tree. You see, that's slightly different than some other parts of the country. And this is what we call a parking lot, right? This is very real. And this is what we call a bicycle ride. El Tour de Tucson every year draws about 10,000 cyclists from all over the place. This is quite an event. And this is what we call September, 104 degrees. That's exactly right. Well, I work with Raytheon Missile Systems, as Debbie mentioned, and we make interesting and very complex systems, actually, that help make the world a safer place. There's some of the product lines shown there. Raytheon Missile Systems, of course, is part of a larger Raytheon company, which is a technology and innovation leader, some $25 billion, 64,000 employees, growing like crazy. Even out in Tucson, we're building big new buildings to house thousands of new engineers and that sort of thing. So trying to innovate. And we do some kind of fun things, like the real Iron Man suit there that you saw in Popular Science, or being able to shoot down a satellite with a missile. A dead satellite was quite a thing. Or being able to defend against other incoming missiles with missiles, which is essentially like hitting a bullet with another bullet, right? It's kind of an interesting technological and engineering challenge. All right, let's just jump in. I want to take you back as we talk about this subject of intelligent systems and about the user's experience. It's just what Debbie introduced here. Let's go back to a time. Anybody remember this kind of device? Anybody old enough? Yeah. This was in the days when we had to adapt to the computers, didn't we? The computers didn't adapt to us. We had to adapt to the way they wanted information. And the way they wanted information in these days was what? One key press, one character at a time. And that's the way we had to give it to them. Or one little punch paper tape at a time. Or maybe a little more advanced, one screen at a time, right? Where you had to fill in all the blanks on the screen, submit the whole screen. The computer processed it and gave you back all the errors on that screen. You know, this was us adapting to the way the computers wanted to work because of their limited data storage, processing power, and data communication speed. Well, things are not that way anymore. Moore's Law, which you're all familiar with, I'm sure, is alive and well. There's been some recent research that says it's still going strong. Despite the fact of rumors of its early demise, we're still progressing in terms of compute power, memory, and storage and everything. So we have all this power. What are we going to do with it? Well, Moore's Law has been progressing for many years, right? And some have even projected it well before the time when Gordon Moore coined it, right? And it still works all the way back in history. So we think it's going to continue for a long time. And obviously, we've used this power to make a lot of progress. You know, this is 25 years ago, a little program called Q&A for DOS. Anybody remember this one? It was a wonderful form-based, generalized database kind of program that you could put together things. And you had to fill in the information one field at a time, move from field to field, fill it out exactly the way the computer wanted it for the convenience of the computer. Of course, now 25 years later, we have forms like Amazon, which, they're the same thing. Still one field at a time, very carefully fill it out exactly the way the computer wants it. So maybe not so much progress there. Well, Garry Kasparov, have you heard of him? He's the world chess champion for some 20 years. Famously, his reign in World Chess Championship spanned the time from when computer chess was a toy and wasn't competitive at all, to when it was a contender, to when it became a champion, to when now it's, you know, something else, right? That's very interesting. So he wrote a book just last year, this book called Deep Thinking, which I highly recommend. A wonderful book. Whether you like chess or not, it's a fascinating read. He looks back on his tournament, you know, his two matches against Deep Blue, which was, of course, the IBM computer that ultimately defeated the world chess champion and kind of set the new bar for that. Well, an interesting comment in the media was that Deep Blue doesn't play chess by thinking. Isn't that shocking, right? It does, but it's literally true, isn't it? If you know how Deep Blue works, it doesn't play chess the way we play chess. It doesn't play chess the way Kasparov plays chess. It does something very different. This is a clue to where we're going. So what Kasparov says now is, with so much power being brought by the machines, we have to find the refuge in our humanity. And where is that refuge? Well, it's in our creativity and our intuition and our strategy. See, Kasparov invented something new. It was a new kind of chess. He called it unlimited chess. So we had these unlimited chess tournaments. And who could enter an unlimited chess tournament? Well, a human or a computer or what else? A human plus a computer, a team could enter this thing. And what always won those tournaments? The human plus the machine. Well, this is very interesting, right? So we can't yet build the machine that replaces the human, but the machine can be the partner to the human. This is what we're going after now with intelligent systems, is they become intelligent partners. So as Kasparov puts it, this is a new form of collaboration where we recognize what we're good at and not interfere with the machines where they're superior. Right? See, the computer and the human together do different things, right? The human brings the strategy, the computer does the mathematical look ahead and so forth, even if it hurts our pride. So we're not trying to build systems that work like us, but that work with us. Now, the state of the art of this is not particularly advanced. We still are mostly in the area, these are some military robots, which can do some amazing things. Here's one that can walk up walls. Here's one that can throw out the first pitch at a baseball game, as well as detecting, explosives and so forth. Here's a robotic dog that can crawl over rocks. Isn't that amazing? But notice there's a human operator in each case driving the thing, right? So the level of partnership between the human and the machine is not all that advanced, right? It's sort of a remote control type device, still very useful. So what are we trying to do? When we say we're trying to build intelligent systems and grow into the intelligent systems area, what does this mean? Well, it doesn't mean that we want a system that works like we do. It works the way we do, that it thinks like we do. Anybody in favor of that? There are projects that are trying to do that. That is very difficult, very speculative, where we wonder whether that will ever be possible. But maybe what we need instead of that is a system that seems intelligent to us, that seems intelligent in the way it interacts with us, that it becomes an intelligent kind of partner. When you talk to people around here or anywhere, don't you form a sort of mental picture of the intelligence of the system you're interacting with, right? And you know what I mean, right? And so for example, let me take a safer example. We get off that territory. Say, for example, is the child. If you're talking to a young child, they have a certain intelligence, I don't mean intelligence level, but experience level. Their vocabulary is more limited. You have to talk to them in a little bit different way and so forth. And then you interact in a more intelligent way with other beings and things, right? So this is kind of the concept that we want to bring to thinking about how we interact with systems. Intelligence, by the way, in case you're saying, well, yeah, Mark, it depends how you define intelligence. Well, intelligence is the ability to acquire and apply knowledge and skills. So do computers already have that? Do they already meet that definition? Sure. Does Deep Blue meet that in the area of chess? Can it acquire knowledge and apply skills? Yes, and it can play chess better than any human. So see, intelligence becomes kind of a continuum. In fact, if we were to map that continuum a little bit, hit the button again, there we go. We could relate it to vocabulary size. This is simply a graph of vocabulary growth for a human being as a function of age. And you notice that it grows very steeply at the beginning. So in most cases, as Wittgenstein, who is a philosopher of language, puts it, the meaning of a word is its use. So it's not that computers need to understand in some esoteric human way the meaning of a word. It needs to be able to use the word. The computer's use of the word in interaction has to be right. So I call it the hi, how are you test. I got to test a few years ago a conversational system for a company. I won't mention what company it was built it. And the first thing I said to it was, hi, how are you? And you know what it said back? It said, I'm sorry, I don't understand. Well, this is, how old does a human need to be to understand, hi, how are you, and give a sensible response to it? Pretty young, right? And does that young human who can respond to, hi, how are you, do they understand the grammar and the specific meanings of those words? No, they don't. They've learned to respond to that. That's how humans learn. So we need to think about progressing systems the same way. So a conversational system should be able to respond to, hi, how are you, right? By the way, John McCarthy said something very intriguing. He said, as soon as something works in practice, we don't call it AI anymore. See, isn't that interesting? So we don't call chess AI. There was a day when we said, oh, if we can get a computer to play chess, that will be generalized intelligence. We'll have a computer that will be just as intelligent as humans if it can play chess. Well, that turned out to be completely false. Right? There's a computer that can play chess just fine. It doesn't have all the other human qualities. So we don't even think of it as AI anymore. We think of it as clever database processing. In fact, just to go back to Kasparov, you know what he said the one thing was that propelled computer chess up the ranks to becoming grandmaster and beyond level? What was the one thing? Anybody want to guess? Was it clever chess algorithms? No, it was memory and storage and processing power. Isn't that mundane? He says that's what brought the power in computer chess, was processing power. Isn't that intriguing? All right, well, anybody seen this movie called Her, starring Joaquin Phoenix a number of years ago? If you're into artificial intelligence and conversation, you've got to watch this. In fact, if you can't stand watching the whole movie, just go onto YouTube and search for Her installing Samantha. So Samantha is the artificial intelligent operating system that Joaquin Phoenix's character starts interacting with in a very interesting way. And she starts saying things, she starts out by saying, hello, I'm here. That's the prompt. How's that for conversational, right? It's human-like. And she says things like, it's very nice to meet you. I have intuition. I'm evolving, and so on. And as you see their sort of relationship, you could say, evolving, it becomes an intelligent presence. Well, that's very intriguing. There's a bunch of movies like that. But there's still quite a large gap, isn't there, between what we experience today in our systems, like Google search. And Google search has a certain amount of intelligence, doesn't it? You can ask it a question, and a lot of times it'll give you the answer. Not just search results, it'll actually give you the answer. So that's got something going for it. Or Amazon.com, or Android, or the Amazon Echo, and so forth. But there's still a large gap between that we're experiencing today and what the science fiction futurist writers, Imagineers, right, imagine in computers like on the Enterprise and Samantha and Jarvis, which was Iron Man, Tony Stark, Iron Man's AI, right, or HAL from 2001 and so on. There's a long way to go. So what is that gap? In fact, it's interesting, by the way, any Star Trek fans here, have you ever noticed that the computer on Captain Kirk's Enterprise, the original series, back in the 60s, that computer was much more advanced than the computer on the later generations of the Star Trek series, which was hundreds of years later in the timeline. So because, Kirk, you remember Kirk and Spock, right? They could say, correlate all possible data related to all events related to this thing that just happened, and correlate all possible theories and come up with a conclusion. And Majel Barrett's voice would give them a conclusion. Well, by the time the 80s came along and Picard's ship and all that, the people had realized computers aren't going to be able to work that way. So they backed it off. And Picard's ship was a lot less advanced, apparently, somehow, than Kirk's ship. So I always find that amusing, right? So what is going to bridge this gap? Well, I say the bridging of this gap is the engineering of intelligent systems. And I think this is something quite different and distinct from artificial intelligence, machine learning algorithms, things like that. What is the engineering of intelligent systems that's going to get us to that kind of experience? Well, first let me mention what I mean by systems. This comes from systems science and systems thinking. There are types of systems. So engineered systems are systems that we build, that we engineer, that we design, like planes and ships and missiles and cars and smartphones and computers and things like that. So those are engineered systems. Human activity systems are systems that involve humans, that are motivated and move primarily by human choice and human decision. So an organization, a family, a company, a country, an economy, all of those things are human activity systems. They include machines, right? But they're a different kind of system. So when we're talking about an intelligent system, we don't just mean intelligent engineered systems. We mean intelligent human activity systems, and we'll get some examples. And the third kind of system, by the way, for the complete categorization here is our natural or biological systems, like humans and animals and forests and planets, you could call those natural systems, and they have their own mechanisms and so forth. In fact, the originator of systems theory was a biologist, and that's where we sort of learned from that. So a system need not function the way we do or even contain artificial intelligence or machine learning algorithms in order to interact intelligently with us. That's kind of the point. If you want one phrase from the whole talk, there it is right there. Therefore, a system might not use AI or machine learning, but still come across as intelligent. Conversely, a system might use artificial intelligence and machine learning algorithms, but not come across as intelligent. So what are we going to do with this? Well, we could try to define something called intelligent systems engineering. The top paragraph is the definition of systems engineering from INCOSE, and it talks about defining needs and documenting requirements. Sounds exciting, right? I like the second one, which talks about understanding needs. And which is easier, documenting needs that we've just asked users for, or really understanding their needs? Turns out humans are actually pretty bad at knowing our needs and communicating our needs, aren't we? Right? So if we're going to design something, we have to try to understand the needs of the user and then engineer and design an intelligent system to meet those needs. So the point is not to use AI techniques and algorithms. The point is to design intelligent systems. So let's take an example here. McDonald's, have you seen these? These are ordering kiosks in the front part of McDonald's in some of the restaurants. They're rolling these out nationwide. But it's not just the presence of the kiosk, it's the whole system. The assumption is, these are taking away these low-skilled, cashier jobs at McDonald's. They're not really, but it does change the system. When you walk into a McDonald's like this, I did the other day in Arizona, and you walk in, there's a very short counter. There's not the big row of people anymore, and there's a host that comes up, a very professional kind of person, says, "Hi, welcome, here's all the kiosks, you can order here. If you got any questions, let me know." A very different kind of person than is usually behind the counter, see? So already I kind of like the experience better. And what's interesting here is the writer, Hollis Johnson points out in this article that what restaurants are struggling with is to hire and retain and train these customer service people, the frontline people. So therefore, and what kind of customer experience do these people give your customer if you're struggling to hire them and retain them? To me, what that says is they're not very well trained. They may be gone tomorrow. Maybe they're not giving my customer the best experience. Maybe the combination of a host and these kiosks will give my customer a more intelligent experience, right? So is McDonald's developing sort of a more intelligent restaurant with the kiosk just being part of it, but they're thinking through the whole system. Number of other examples, and you've seen other restaurants kind of starting to adopt this. It still drives me crazy that still in the vast majority of restaurants today, if you want your drink refilled, what do? Well, of course, you push a button on the table. I mean, we're an automated society. Who has that? They don't have that. You can't even signal for the drink, right? Isn't that interesting? All right. There's a restaurant called Stacked, by the way, you may want to look at. They're in the West Coast. They're totally on this model. They don't have waiters at all. You go in, you sit down, they seat you at a table, you have a kiosk. Up comes a host, almost like a restaurant manager, who says, here's the kiosk, here's how you work it, and so forth. And then they bring you food out and so forth. It's a very interesting experience. All right, we think about it, automated driving. Did we mention the auto industry? This is the model from the Society of Automotive Engineers of the range of intelligence and automation brought by automated driving capabilities. But what we need to think about, though, is are we increasing the baseline? So here's the baseline of intelligence of the driver plus the car. Aren't you driving your car together in an intelligent system? Let's hope, right? At some level. But can we add to that with the intelligence? Not can we replace it, but how do we add to it? And where's the goal? What are we trying to get to? Full automation as the goal? No. We're trying to get to the experience of going somewhere as that of having a chauffeur. Wouldn't that be the ultimate, right? If you had a personal chauffeur that not only drove the car, but had a certain intelligent interaction with you and could help you and serve you, meet your needs, and that sort of thing, right? So that's what we're trying to do, is design that kind of experience through the whole system. And it may involve other humans even as well. All right, so I want to finish up in the last few minutes here by throwing out a few possible principles of engineering intelligent systems. This is not a final set. This is kind of an early draft, right? Work in progress. But see if this helps a little bit. So first principle, when you're designing a conversational system, think Play-Doh, not Plato, right? And what do I mean? I mean, take into account the stages of language learning. So when we learn a language, whether it's our original language as a child or whether we're learning a second language later in life, we go through stages of learning that language. Some of the first things are knowing what alphabets and numbers and essential information mean, and then we proceed to short phrases. Hi, how are you? Where's the bathroom? The important phrases that you learn when you're learning another language, right? And then you get to more grammar, understanding more phrases, increasing vocabulary, and ultimately thinking in that new language, don't we? Right? Eventually, you can get to where you're thinking in language. And some people tell me if they speak multiple languages completely fluently, that they actually are like different people. They're a different person when they're operating in that other language. That's very interesting. So how does this apply to intelligent systems? Well, can we engineer systems to at least be able to understand basic concepts first, right? This is the hi, how are you test, right? So can we make it interact like a 2-year-old before we try to make it understand fully complex sentences? So it's, again, things like the Echo and other conversational systems, you expect them to be able to do basic interaction. All right, a couple more principles here. Think improv, not Jeopardy. So playing Jeopardy is wonderful, and of course Watson became famous for being able to play Jeopardy and understand those clues and so forth. But in a conversational system, you want to think more improv than strictly worded clues like Jeopardy does. For one thing, those Jeopardy clues were very specific and were very carefully worded. That was an advantage that Watson had, right? There wasn't a lot of mess in it. They were worded intentionally, right? But in improv, there's a rule. If anybody ever done improv theater, right, there's a rule that says you always go with what the other person says. You never say no. If someone says, look, is that a bird up there? The other person doesn't say no, they say yes, and it looks like it's pulling that airplane. You expand on whatever the person says. You find something in what they've said to respond to. So we need to make our systems do that and interpret things favorably. So next principle, context is king. The system should be aware of where it is, who it is, and what it's interacting with. If I say, I want a table, that should produce one response if I'm talking to a system in a restaurant, and a very different response if I'm talking to a system that's in a furniture store, right? So what is the context? What does a table mean? This is something humans get sort of naturally. All right, coddle the beginner, reward the experienced user. Systems should be designed to help the beginner user, take them along step by step, bring them along very carefully, just as you would a child, or just as you would if you were teaching someone a new concept. But it should also reward the expert user with very fast key presses, function keys like the old hotel desk check-in systems used to use, and allow experienced users to do things very fast. So final principle here is teach systems self-care. And some systems do this to some extent, but we should teach systems to check themselves, test themselves, maintain themselves, and even repair themselves if possible. We do this a little bit in missile systems, right? Or things like cars now have a sensor for low oil level, not just low oil pressure like it used to, right? But actually when the level is low, it helps you maintain it and so forth. So a single fault shouldn't disable the system. If you notice monitors that can't figure out to look through the sources to see where the source is, you have to manually select it, right? All right, so I'll just wrap up here. And what I encourage us to think about as we think about this journey, and I really think this is just barely the beginning of a journey of thinking about designing intelligent systems, is what do we want our systems to be? What is the right sort of human paradigm or metaphor? We often think of them as slaves that we give simple commands to and they carry them out because they're just dumb slaves. That's not the right kind of image. What the right image is assistants, partners, a personal assistant. And sometimes your personal assistant might be an attorney. They might know more than you do, but they're still an assistant to you, or a chauffeur, or what is the right paradigm for how we want to act these in intelligent systems. Okay, so we'll leave it there, and thank you very much.